or essentially what's called the Bohr compactification of the real line. I'll say a little bit more about this on the next few lines here. So this Hilbert space is defined with this inner product here. So we have, P was the densitized triad component, so we're looking for a momentum representation here. And the inner product is not obtained by integrating over P, even though P is a continuous parameter, but summing over P. So that's tricky if it's a continuous parameter, but normalizable states are such that only at most a countable number of the psi P components are non-zero. So for an actual pair of states in the Hilbert space, it is maybe a power series or maybe even a finite sum. So it's well defined. And then on this space, we act with this exponential, or the polynomial type operator, by just shifting the label. And now one can check that the P operator has a discrete spectrum. So I don't have this equation here, but so it just reproduces P. So it's like the momentum operator and the momentum representation. So it reproduces P, so that's the eigenvalue. P is a real number essentially, so we would think it's a continuous spectrum, but then in this Hilbert space, each state psi P is normalizable. Because if psi P means this psi P here, that it is non-zero only on an individual P, so you have just a single term in the sum here. So you have normalizable eigenstates, and then in this sense you have a discrete spectrum. So that's the difference with the new Hilbert space here compared with the standard quantum mechanics. So in this case we just used a C. In cosmology it's usually better to use the Hubble parameter instead of A dot, which is what C would give us. So before we actually quantize, in most cases, we do a canonical transformation and go from CP to H, the Hubble parameter, and the volume. And then we'd actually have polynomials as functions of H instead of C. And but it's then the same idea. So each then we write the sine function in modified Hamiltonians or frequent equations as a combination of exponentials. Each of them shifts the eigenvalue. So if we quantize this expression, we get a difference equation, which we can solve. So that's how one can derive wave functions. Now there's a way for some models which is actually very close to the harmonic oscillator in quantum mechanics in terms of some mathematical features. The actual dynamics are different, but some of the mathematical features are similar. And so instead of talking about wave functions, we can use a more algebraic perspective, which we also use for the harmonic oscillator. So that's our modified frequent equation of the sine function. And now if we deparameterize, or first we specify the energy density to be from a free massless scalar. So it's just a kinetic term, d phi squared over v squared. And now we can use this phi to deparameterize. So we use phi as an internal time. And that means the momentum of phi, which appears here, will then generate evolution. So if we solve this equation for p phi, then it actually simplifies. So we multiply with v squared and take a square root, so it's just v times the sine of LH, or the imaginary part of this product here. So the Hamiltonian, this p phi, as an internal time Hamiltonian, is now linear in J. And if you work out the Poisson brackets, or if you have some operators, commutators, V and J also have linear brackets, so V and the real and the imaginary part. So they form the Lie algebra as L2R. And the Hamiltonian is linear in these variables. So you have something which is very similar to the harmonic oscillator, which then if you go to equations of motion, it implies that you don't have quantum back reactions. So you have the closed set of equations of motion for just the expectation values of these coordinates here on phase space. and they don't couple to fluctuations or higher moments. And then the fluctuations are only coupled among each other, so don't couple to higher moments. So the corresponding canonical effective equations can be solved. There's only one additional condition, which classically looks like this. We have to make sure that h in here is actually a real number, so we can't use arbitrary complex numbers for j. But if this equation is satisfied, which would just be the cosine of this SL2R, and then we set equal to 0, that means that h is a real number. So if we solve these equations of motion, we get a cosh function here. So again, this indicates the bounds. So the volume as a function of this internal time has a non-zero, a positive minimum from the cosh function. And if you go to higher orders, you can check that the volume fluctuations divided by the volume remain constant. So the state doesn't really get more quantum as the volume changes, because this ratio here, which is a dimensionless measure of quantum fluctuations, remains constant in this model. So it's also like the harmonic oscillator. You have something like coherent, dynamical coherent states which don't spread out too much. Now, there are few subtleties after quantization, because if we quantize this condition, it's quadratic. So it does couple expectation values to fluctuations, if you just take an expectation value of these terms. And so the expectation values are related by some fluctuation and a covariance term here. Now that implies that if we now go through the derivation of an effective Riemann equation just like before, so try to remove all the C, or in this case the J dependence, it turns out we have to use this effective reality condition, and so the previous rho square term has an extra fluctuation contribution. So it's not exactly quantum back reaction, but fluctuations do contribute. But not too much in this model. So we can still, it would just imply that the bounce density is shifted a little bit, because now rho plus sigma has to be equal to the Planck density instead of just rho. It doesn't eliminate the bounce in this model. But then if we include maybe matter interactions, not just the free master scalar or anisotropies and inhomogeneity, then we do get quantum back reaction, because that's like going to an anharmonic system instead of the harmonic oscillator. And then it's much more complicated to understand the generic dynamics, and we're back to the problem of states, because then quantum back reaction depends on the fluctuations, and that depends on the initial state. So these models, then it's more difficult. So that was the first part. And
how do you make sure you preserve the relative condition as times go?
So classically, that's actually the cosine of this SL2R in these variables, which means it has zero Poisson brackets with V and J. So Hamiltonian equations classically preserve this function. So if it's zero initially, it's always zero. And then if you just use a quantum version of SL2R, so that's a different version of angular momentum operators, then this combination here with the specific ordering now has zero commutators with V and J dagger. So if you compute Heisenberg equations of motion, this combination has a zero time derivative. So it stays zero. So you have to impose the reality condition only for the initial state. And then you can let it evolve, and it will always be obeyed. Are there more questions about loops? Because I'm now switching. Not yet, but Heisenberg spin chain. I mean, we started with the initially, we didn't actually notice it's the Heisenberg spin chain, but we just tried to come up with a simplified version of the SU2 spin network situation. So we just had a bunch of spin or angular momentum operators, and we tried to find a simple coupling, which eventually, after some reductions, turned out to be the Heisenberg spin chain. So, and these reductions are the reason why maybe the notation is a little bit confusing initially. These i's here there's a finite number of spins, and we have a spin chain. And initially we actually had vertices, so it looked more like a graph where you have interactions between different spins meeting in vertices. But then we imposed a constraint and reduced it, and what's left were just a one-dimensional spin chain. And because we reduced it by eliminating even numbers, the actual labels of the spins are just the odd numbers. So just keep this in mind in the next few slides. So I goes from 1 to n, but then in the labels we have only odd numbers. So there are two terms here which are not very interesting, which are just squares of angular momenta which commute with everything, so they don't really do much, but we left them in the system. And then there are next neighbor interactions. So J1 times J3, for instance, and so on. And that part would be the Heisenberg spin chain, the simplest version. And so then we introduced mini superspace Hamiltonians. So we wanted to analyze the mini superspace approximation. And the simplest version would be just setting all the J operators equal to each other. So there's really just a single J, but n times, because initially there were n spins. Now that mini superspace model is also not interesting because again there's just this J squared which commutes with everything, so there are no interactions in here. But then there are two different versions of mini superspace models in which we leave two independent spins in the system instead of n. And the first version, so these are alternating odd numbers here. So we, let's see, so in the first version, then we identify J1, J5, and so on. So it would be JH1. And we identify the remaining strings. So JH1, JH2 are independent, but these are the only two spins left. And so then we can see, just inserted in here, there's no interaction term, so that's the more interesting dynamics. And the next one, the third mini superspace Hamiltonian, identifies the first half as one spin and then the second half as the other spin. So that is something which in cosmology might seem more natural. It's a little bit like what's called the separate universe approach. So sometimes people approximate inhomogeneous configurations in cosmology by patching together homogeneous slices, or just in space, or homogeneous regions in a single spatial slice. So that's a little bit like the second the third mini superspace model, which also is interacting. And the interaction terms are very similar, but the non-interacting ones have opposite signs if n is greater than 3 here. They don't matter too much because these are not interactions, but still turns out there's a big difference between these two models. So in cosmology, one might think that the third version might be the most useful one. If you know a little bit about the Heisenberg spin chain, it's used to study ferromagnetic and antiferromagnetic materials. So if you have antiferromagnetic behavior, that means that spins on two neighboring sites have to be antiparallel aligned. And that corresponds more to the second mini superspace model here. So in this situation, that's actually a better approximation, and we'll see this in more detail on the next few slides. We'll derive properties of ground state. So again, H1 we just ignore at this point because there are no interactions. H2 and H3 are both of the same form, but different signs. Again, doesn't matter too much. Now, to compute the ground states, first using just standard angular momenta in quantum mechanics, we have to couple the two spins to the total spin, as usual, and then try to minimize it, or find eigenstates of this H here with the smallest eigenvalue. If gamma is positive, then we can minimize the interaction by the antiparallel configuration, so that would be the singlet combination of the two states. And then this standard identity from quantum mechanics for the total spin, in terms of individual spins, gives us this eigenvalue. If gamma is negative, the minimum is for parallel spins, and there's no unique ground state. We have the full multiples of the maximum spin, and gives us these eigenvalues. So that's the same for both models, but then for different signs of gamma or the original alpha here, we get different behaviors. So this would be antiferromagnetic and this would be ferromagnetic. Now canonical is vector potential, so we can also test these methods in this context. So as we've seen in the other models, it's useful to use uncertainty relations because that helps us a little bit with these minimization problems. So in this case, non-canonical operators, and so that means there's an expectation value on the right-hand side. But we still have a standard type uncertainty relation. And now we can also assume that the expectation value of j points in the z direction because we haven't fixed anything about our coordinate axis so far. So only jz is non-zero. And that means that the two other uncertainty relations are cyclic permutations where we have jx or jy or just zeros on the right-hand side. They imply that the jz fluctuation has to be equal to 0. And then the remaining equation, so jz is then equal to j in terms of the expectation value, gives us a relationship for the jx and jy fluctuations. By rotational symmetry, they should be equal. So we get all three fluctuations in the effective potential of the first mini-superspace Hamiltonian. So again, that was just j squared. So the fluctuation terms are just the the fluctuations of the three components. So if we insert these values here, it's just h bar times the jz expectation value, and if we combine this with the original, just the classical term here, then we get also the correct s times s plus 1, which we know is the eigenvalue of j squared. So that's another test of these effective methods. For the interacting models, it's slightly more tricky, but we also get the right results. So in this case, we have two spins, which means there's an additional uncertainty relation for two actually commuting operators. So h1 and h2 are independent spins. So their commutator is 0, so normally we would call this an uncertainty relation, but it still gives us an inequality between fluctuations and the covariance. And these fluctuations appear, and even the covariance appears in some of this effective Hamiltonian. So also here the classical terms, just expectation values, instead of the classical variables for the quadratic term and the interactions, and then plus fluctuation and covariance terms. So if also two cases, if gamma is positive, we can minimize the covariance terms in the Hamiltonian by using the most negative solution for the covariance of this saturation equation. So that relates it to jz. And if you go through the details, you get the same expression that we got from the antiparallel of the spin singlet state previously, and if gamma is negative, you can also reproduce the previous energy, the ground state energy. Now, comparison with the full theory. So we know this in this case. People have done a lot about Heisenberg spin change. And as I mentioned, there's really different physics for different signs of gamma. And the corresponding configuration of the full theory has to be, if it's antiferromagnetic, it has to be alternating spins. So that's captured only by H2. And H3, if we have antiparallel alignment, we would have spin up in the left half and spin down on the right, and that's not antiferromagnetic. It's not even a well-defined ground state or energy eigenstate of the spin chain. And one can also, if we just use for the effective equations, one can show that even though the mini-superspace model has a ground state for H3, it is not stable, and I made a mistake here. It's actually, we can test it at the mini-superspace level, but we can still test it semi-classically. So we can try to embed these mini-superspace models into a full chain. semi-classical using moments, and then if H3 is unstable, H2 is stable. So in this way we can, even if we didn't know about antiferromagnetism, we would still be able to distinguish these two different mini-superspace models. But even H2 is tricky, or the Heisenberg spin chain is actually tricky, and there's just one example. If n is equal to 3, so our full theory would have 3 spins, our mini-superspace model 2 spins. It's not much of a reduction. But in this case, you have an 8x8 or an 8-dimensional state space. You get an 8x8 matrix for your Hamiltonian, which you can minimize. It's a little bit of work. And you get these two states. There's no unique ground state in this case. That usually happens if you have an odd number of spins in the spin chain. And it's not exactly what we might expect. So it's not just a single one of these, where is it, like the central state here, which is really alternating, so plus 1/2, negative 1/2, plus 1/2. But then we have to add contributions which are not of this form. So the ground state is not, it's not the simple classical expectation of an antiferromagnetic state, which would be called the Niel state. So it's slightly more complicated. And if we use this state to compute the moments exactly, not in this semi-classical picture, there are differences here, or not in the mini-superspace model, but in the full theory, we get these expectation values, so they are kind of anti-parallel opposite signs on 1 and 5 compared with 3, but the numerical factors are also different. So that is something which is not captured by the second mini-superspace model. And if we compute fluctuations and covariances, there's some differences too, and even some next to next neighbor covariances are non-zero, which we would not expect in the mini-superspace model. So there's some very detailed results, and that's a Heisenberg spin chain paper, which actually did introduce this H2. They didn't call it mini-superspace, but AB model for some reason. And they did lots of numerics and compared these physical results in the model with results in a full spin chain for different, even larger numbers of n than just n equal to 3. So there's still a lot that one can learn about the mini-superspace approximation from these results. And then finally, quantum chemistry, and it's really mathematical, but quantum chemistry gave us a suggestion about a reformulation of this moment system, which is pretty complicated. I haven't shown this Poisson bracket yet, but I mentioned it can be computed exactly, and unlike a single Q and P, which is just equal to 1, it's really complicated. It's quadratic in the moments on the right-hand side, and if you have high orders, then there's really a large series, still finite, but lots of terms on the right-hand side. So it's a Poisson manifold, has a Poisson bracket, but it's not a simple one. Now, since it's a Poisson manifold, there are mathematical theorems which tell us we can always find so-called Casimir-Darboux variables which are canonical. So there's some Q's and P's which have the standard canonical brackets, just a new set of coordinates on the phase space. And maybe also some C's, Casimir functions, which Poisson commute with everything else. So these are existence theorems. They don't tell us how to construct those. But if we can find them, it's very useful because it will dramatically simplify these brackets. And that's where quantum chemistry helped us. Not actual chemistry in the lab, but there's a quantum chemistry review here. They call it quantized Hamiltonian dynamics, which is almost the same as canonical effective theory. And they had an additional construction, which is a canonical reformulation of the second order moment. So fluctuation and the covariance, just written like this. And then one can check that the Poisson brackets of these moments are equivalent to a single canonical bracket between Q1 and P1. And C, this combination commutes with everything else. We have a zero Poisson bracket. So that's the Casimir function. And that gives us a much nicer description of effective Hamiltonians to second order. So previously we used these expressions, so these Taylor expansions up to second order. And now if we insert these reformulations or transformations of the fluctuations, we get just a second standard kinetic term instead of delta p squared. A new potential from this C over Q1 squared here, and an interaction term. So it's really just now a two-dimensional classical system. Now the quantum chemistry people did not tried to extend this to higher orders, but two grad students at Penn State worked really hard and found an extension to fourth order for now, and they tell me they can extend it to arbitrary orders in principle. So for fourth order, we need to include their 5 canonical pairs. So that's it's easy to compute the number of moments at each order, so you have an expectation on how many degrees of freedom you should expect. And so for fourth order in the moments, there will be 5 canonical pairs and 2 Casimir functions. And so now we could expand this to fourth order and insert these values, which gets really lengthy, but each term, notice that delta p squared just has a bunch of p squareds and then the potential. So each of the new variables or new degrees of freedom will just contribute a standard kinetic term and additional, in this case, higher order polynomial corrections to the potential. And so that's a much more standard dynamical system, which one can analyze in terms of fixed point, for instance, or other things. And for the numerics, maybe also for analytical solutions, it's much more convenient. And the example that we have so far, that's actually a plot which is very similar to this quantum chemistry review, but we reproduced it using the canonical formulation up to third order. And as you can see, don't have a plot for the potential, but the basic features, it's a cubic potential. The classical potential, and let's see, so at 1, has a local minimum at 0 and a local maximum at -2, and then it goes to negative infinity on the left, and at q equal to 1 it has the same value as the local maximum, and then it goes out to positive infinity. So we talk about the classical curve first in green. The initial conditions are such that we just choose an initial position and the initial zero velocity. So we just put the particle right on the potential line in terms of its energy. So classically, if we start at a value greater than 1, we have enough energy to move across the local maximum and reach negative infinity. That's not tunneling, but the way we define the tunneling time, it's still a finite value here. If the initial position is less than 1, we do not, we don't get to negative infinity classically. So the tunneling time shoots up to infinity because there's no classical tunneling. Now the exact values in quantum mechanics using wave functions are the stars here. So for any position, there's a finite tunneling time, and its greatest at the minimum. That's what we should expect. Now if we use these effective potentials here, so a two-dimensional system, to second order in red, we get more tunneling than in the classical description, but there's still a range around 0 and a little bit to the left where we have an infinite tunneling time. So it doesn't give us the full picture. So to this order, we don't expect that the particle can escape under all circumstances. But if we go to third order, so that brings in the new parameterization, you're not excluding fourth order, because it turns out third order is enough. We get a finite tunneling time always, and it's pretty close to the exact values from the wave function. So, and I think in quantum chemistry there are examples where maybe a molecule breaks apart into two smaller molecules, and in some cases that is a tunneling example. So that's why it came up in this context. But now it's for us it's encouraging because it really tells us that these effective methods are correct. It's always an approximation, but it can capture the physical effects. So to conclude, the main point I tried to point out here was that we have to go beyond mini-super space models, and we have a few different ideas and a few results, but certainly not correct. So we don't really know what they tell us about the full theory. But that's why these analog systems, like the Heisenberg spin chain in quantum chemistry and maybe others, are interesting because they are more mainstream physics. They're better understood, and they can at least help us to test the methods. In terms of cosmology, so for the last few lectures, of course, there are many open questions. So the three problems are the problem of states, time, and covariance. So these are the big problems, which are decades old. So it's not just lukewarm gravity, but canonical gravity in general. And some of them have really led, when we try to solve them, like covariance, we